Learn physics with J Science.
Hello there, welcome to another lesson. In this lesson, I'm going to show you how simple harmonic motion works. It's more of an introduction to the concept. Now, take you guys a little bit backwards. In physics, we have different kinds of motion. You have the linear motion, you have the oscillatory motion, you have the circular motion, and you have simple harmonic motion. Now, simple harmonic motion is more like a stem off from circular motion. So in SHM, as it's fondly called, you have the particles moving back and forth, a repetitive movement. A very, very typical example of that is a spring you have on your screen right about now that performs vertical motion, or what we can say that simple harmonic motion in line with the vertical axis. And the second example you have here, which is the pendulum. Okay, I'm sure some of you have seen the pendulum, how it works in the lab. Pendulum moves from left to right. Okay, and there's one thing I want to point out. That movement of both the spring and the pendulum, they usually have like a midpoint, or what we call an equilibrium position. Now, what happens here is that the acceleration and the force is usually directed towards that fixed point. So what they are trying to do is to get back to that equilibrium position. Let's look at the pendulum. If you have the pendulum moving towards the right, yeah, that would be my right here. You have it as positive. Let's say this is positive and this is negative axis. Now, once it moves from the equilibrium position, like we just move to the right, once it gets to that plus area, it comes back to the equilibrium position. Now, the force that brings it back to the equilibrium position, we'll call that force the restoring force. And you can also relate that to the spring as well. Once you have a mass hung on the spring and you compress the stuff, it comes down, coming back to the rest position. That's the equilibrium position here. The force bringing it back, we call it the restoring force. And in this case, is the formula is minus kx. Okay, your k is a constant. Let's start from here. Like F is directly proportional to the displacement, because as the restoring force increases, the displacement also increases. We can link it up to our Newtonian physics, that's Newton's second law of motion. This is F equals ma. Since F equals ma and F equals minus k, that's the spring constant. When we remove the sign of constant proportionality, you introduce your k, which is the constant, the spring constant. So this will be equal to minus kx. The acceleration, when I talk about the acceleration, I'm also talking about the force in this case. So I can use those terms interchangeably. They are not the same thing, but because the acceleration multiplied by the mass will give us, the acceleration multiplied by the mass will equal the force. So that's why I tend to use them interchangeably. There is a connection between circular motion and simple harmonic motion. In fact, they are closely related. Remember what I said earlier, that it's like a stem off. Now you have a diagram here, you have the imaginary circle. Now let's assume that we have a particle at this point. Just follow my pointer. You have a particle at this point performing a simple harmonic motion, and the particle that's from this midpoint down to point R is moving with a certain speed, and we can quantify that speed as v, right? Let me just put the speed so that you guys can understand. Now, since angles are involved, right, the idea of angular velocity comes into play. That's your omega there. And the link between the speed and the angular velocity is the angular velocity multiplied by a, the amplitude. And that amplitude I talked about, which is a, you have it there in the diagram, is also equal to the radius of the circle. So that means we can see that a, which is the amplitude, is equal to, let's say, OC, and that is also equal to SC, and it's also equal to XC, and that is also equal to CY, and all this you can say is the radius. Okay, and remember that A, that's the amplitude. So that's the first relationship I want you guys to understand. All right, now let's do a drop down from R down to B. We call that a projection of R upon that diameter, that's the OS, from O down to S, that's the diameter of this particular circle here. R, that's the particle R moves around the circle. So as R moves around the circle, point B moves to and fro, to and fro. So you have two movements like that. One moving around the circle, that's the particle, and the projection, that's the perpendicular projection we did, moving to and fro. Now that projection stops. Okay, not really stops, just temporarily stops at point O. Once it moves like this, temporarily stops at point O, like rests, then comes back, trying to get back to C, which is the center. And at the center, that's where you have the maximum speed. At the center, it's more like this other one you have, at the center point here, that's where you have the maximum speed at the equilibrium position. So I just want to point that out to you guys. So at the center here, that's where you have the maximum speed. And once it gets to this area, I'm talking about B, then it temporarily stops, then moves again. When the pendulum moves this way, it stops, then moves, stops, moves, like that too. The link that we're talking about here is the displacement. Now remember that we have established the fact that R moves in a circle, that R performs circular motion, and B, that moves to and fro, performs simple harmonic motion. So that's how the stuff works. So if you had to define X, that's the displacement, that's what you have here, then we can say that X, which is the displacement, is equal to the amplitude. Now the amplitude, remember I said, is the maximum displacement. If I have to have this on a wave diagram, this point here, that peak, that's what we refer to as the amplitude. So our business here is the maximum displacement of the particle, and that, which is A, which is the maximum displacement, can be said to be equal to, that's X, okay, can be said to be equal to A, that's amplitude, cos theta. And lastly, looking at the angle theta that you have here, we can say that as the particle moves from S to X to O to Y, that's around the circle, we're talking about the particle R. At S, we can say that the angle is 0 degrees. At X, we can say the angle theta is 90 degrees. At O, the angle is 180. At Y, the angle is 270 degrees. And back here is either 0 or 360 degrees. And in terms of the displacement x, you can say at S, x is 1, or we say positive 1. At 90, x is 0. At 180 degrees, that's at O, x is minus 1. And at Y, x is 0. Like that. And that can also mean that where we have plus 1, we can have plus A. That's the amplitude. And here we have, that's it guys. Thank you for watching and I'll see you next time.